Okay, for people joining this live stream, we are talking about the future of arrays in Wolfram language, and Rob is going to show us some things. So,
okay, so right. So is that all visible and good and big enough?
Yep.
Excellent, great. Okay, so we've had numbers of discussions, and there's sort of been two thrusts of what we've done. And one, I sort of have worked, thinking of your idea that you talked about rectangular data. So I sort of came from a rectangular point of view. And I think Leonid has worked from a more hierarchical, flattening point of view. And they both sort of come to the same point, this concept of tabular data. So I've also, some of what I've developed, I'm going to show you stuff. And if you get tired of this, you can tell me to move on. But there's also some stuff that I think would just be useful utilities for particular rectangular data outside of the general idea of, an array container or something. So
rectangular data is data that's accessible with part, you say there.
Right. And I've listed some advantages here. So the big advantages are parts or bits of the data are easily changed and accessed. And the disadvantages is if you filter it or select, some based on parts, outside of part, you can break the rectangularity. So, and often, and this model doesn't work very well for hierarchical data as well. So, unless you have a data container inside a data container, and then that gets, I think Leonid has some nicer solutions for that type of thing. Okay, so
missing is not special here. Missing is just some part that might be treated differently by functions that operate on the data, on the content of the data, but missing is still present as a part. Correct.
Missing is still present as a part. That's an important fundamental idea.
Okay. All right. Okay. Fine.
Yeah, that's key. And in fact, so this first simple example I've taken has a missing in it to sort of, try to deal with that, to make sure we're dealing with that in some way. And of course, I've just got really simple examples here to illustrate the principles, not so much the potential. Okay, so this is a rectangular data called rdata1, and a command I put together.
There's a generalization of dimensions that also tells you about associations.
Right. It tells you about associations, and I wrapped association keys in something called key list, partly so it's easy to see, and also you'll see there's another reason why later.
Right. Okay, I get this idea. This is an interesting idea.
Yeah, and this actually is implemented through an additional thing I added to this more recently is the idea of you may want to name levels.
Indeed, we've talked about that. That's an important thing.
And so this data dimension, you specify the levels, and it gives them names. Instead of returning a list, it returns an association with the levels.
But wait a minute. In the actual data thing, right now we do not have a way of naming. I mean, for example, for Dataset, it would be lovely to be able to name levels.
Well, that's coming, Stephen. That's coming. That's part of the idea of the container design.
Okay, fine.
So good. So I figured we get through this. Okay, so this is data it's not rectangular, but it's rectangular-ish. And so if you just do the data dimensions on this by itself, it just gives you 2. Okay, but what I've done is I've set up a version of data dimensions. Now this is toggled by a thing, and what it does is, okay, do I merge? So the reason this is not rectangular is it has different keys at this alpha level. Okay, so A, B, C instead of D, and so it's not rectangular. But if we say, okay, let's merge keys and consider the whole set of keys possible that appear on any given level, and it's exactly the order is consistent with key un, merge, join, and join across. So there are precedents for this, and now we actually get rectangular representation. For
right, but so conceptually, you've got a missing in the places where there was a non-rectangular hole previously. Is that
precisely
correct?
Precisely. And yep. So that's.
So the container, if it part extracted into the whole, it would see a missing.
Yes. Yes. Okay. And that's the concept. Okay. So something we're going to need to work with this data in any efficient way is conversion to what I call list arrays, which are just lists. Okay.
Yep.
And this is sort of like, this is like values on steroids, basically. Okay. Yep. It goes and removes all the keys. So we can remove the keys. We get this. Of course, we save huge amounts of memory. And this is the key. The key thing we can do is we can restore the keys.
Yeah, I got it. I mean, this is the idea of a data container, right? Yeah, so I mean, this is the inner dense data object, which probably in some world of the future could also be an inner sparse data object.
Yes, I think that's another representation that I'm going to get to here. So yeah, so this is so I've written a whole bunch of utilities that work with this that will make putting together this data container much easier. You can also, for example, if you want to change keys, you can change keys by putting in a different data dimensions with different keys. And so here's the case where it was not so rectangular, and so we end up with some missings here.
Yep.
As you would expect. But you can also restore the keys fully, and it, instead of putting the missing, it just on association levels, it just leaves them out, which makes sense. Okay. So,
but by the way, the only thing I would comment about that round tripping is the question of the order of the association elements. When you have, I mean, I don't know whether it's preserving that in the round trip.
Well, it changes it, because otherwise we have to save the ordering.
Okay, fine. So it doesn't preserve it.
It does not preserve it. No. It goes back to that merge keys order, which I think is a reasonable thing to do.
What happens if you have an explicit missing in the association? Is that treated differently?
Yes.
I think that you should have a different key in the missing to represent this kind of. I mean,
it's a missing key absent.
But isn't that the same thing as key absent is different from the case where you have extracted, where you've used lookup, for example, on an association, and you ask for something that isn't there. What do you get in that case?
That's what you get, is missing key absent. When it's
okay, I'm just saying that I think it might be useful to have a different key in the missing to represent this form of implicit key absent. Maybe not. I don't know. You get what I'm saying, though. Okay.
Yeah, I get what you're saying. I think that's a detail. I mean, there's lots of details.
Yeah, that's a detail. So I'm putting that. Okay, let's continue.
No, it's good to get details. Okay, so here's another. So this is the idea of conversion to a list array, which is really useful. But there's also another way, and a lot of our backends are going to use this idea of tabular data, such as query language stuff, arrow data, which I'll be showing an example of later. And so having a conversion to tabular data is also useful. And this is actually, in some ways, a little. It's not as efficient as conversion to list data, but it's also a bit more general too. So
what is tabular data?
Okay, by tabular data, that's why I've shown a bunch of tables here. The idea is it's basically the data flattened to 2D. Okay, and so we take the last dimension here. Okay, and then these appending rows, these are actually the dimensional, listing what the dimension name actually is. So here the index is 1. Here the dimension, this is the alpha key. This is the A key.
Wait a minute. So why are that? So the bottom level is across the columns of this thing.
Right. Yeah.
But so all other levels are just being put as the prefix elements for each row.
Right.
Okay. I mean, it's kind of a hackosaurus, but that, I mean,
well, it is a hackosaurus, but it's quite, it's fairly
compatible
general,
with a lot of other things that
and
have
it's
been
compatible with a lot of other things, and it's somewhat compatible with what I think Leonid is going to talk about as well. So we can also do 2 tabular columns. The reason to do 2 columns, this is just an efficiency hack because we know that these types are all the same. So we could store these in a packed array, or we could store this as a string list if we had such a thing, or a packed
What's
array.
a packed? What types are all the same?
The types across these. So this is just a
each row is the same.
Each row is the same. So we just
I see. So this is a question of the fact that we, because of our data structures being row first, so to speak, we can we can't, the fact that a column is all of the same data type doesn't help us as such in the way that our internal packed array stuff works.
Exactly. And that's how things like this arrow package, for example, and I think a lot of SQL databases work, on having the same type in a column, and then the row covers all of the things. Okay, and then we can, this is just a transpose, as I said, and it works with this not quite rectangular data as well. So here we just have the 3 dimensions, and then we have, these data, and these are actually all data dimensions in this case. But this case I purposely set up is you may want to consider the data as different types, right? You may want to just consider this is a database of 2x2 matrices. And so you can do that by specifying the dimension right. You can do that as well.
Okay, but hold on. As soon as you have a missing, you're going to blow out, unless you have some hack for storing missing, do we have a way of packing missings?
Yes, well, that's one of the things. That's one of the things I'm working. So this arrow package has a way of packing missings very efficiently, which we'll need to integrate better. And I've also set up a way we can develop our own backends, different backends, and almost and there are different ways of packing missings. But yes, a key thing is being able to pack missings, because otherwise we lose any efficiency in storage, right?
Sure. Okay.
So
cool.
that's one of the things I've thought about, what I spent a lot of time thinking about when doing all this. And we can also do conversion from the tabular data back. So we could have, so for example, I can take, the tabular data of this. It's the same from now. I can take, parts which are not necessarily contiguous. So this is not the same as part of the rectangular thing. Okay, but I can still construct, reconstruct that part of the rectangular expression that's left.
Okay. I mean, in other words, with pure part extraction with lists and spans, you are guaranteed to go from a tabular object to a tabular object.
Right.
As opposed to running select or something, which could give you all kinds of random gunk.
Well, no, this could be, this case that I'm showing here could be like a select.
Well, in 1 dimension it could be, but not in 2 dimensions.
Yeah. Right. Right. Okay. Well, I'm getting to an idea of how we can do select that I think Leonid has a more dimensional solution for, but we'll get so so we can convert to the tabular.
I have a point of language here, Rob.
Yes.
Mm-hmm. Leonid is Leonid, not Leonoid, isn't he?
Oh, Leonid. Sorry.
Thanks, Stephen.
That's
just
my
wondering
bad.
about
You should have told me, Leonid.
Well, it was kind of interesting to hear a different version of my name.
Right.
So
okay.
It's
sorry.
Okay. Never mind.
It's all right. It's all right.
It's a lot more functional language, I think, when denoid.
Yeah.
Yes. Right.
Okay, go on. Yeah.
Yeah. Okay. So that's the okay. So now here's the concept, which is the idea of selection from tabular data.
Mm-hmm.
Okay. So here I've set up a data dimensions, and I've purposely given these dimensions, these levels, names. Okay, yep. And you can actually see where the names appear. So now I've set up a function which I call filter, and I can just use, like a function just like select. So this is like select, but I'm now referring to, columns in this tabular data.
Okay, so it's kind of almost like an array select.
Yeah, it's like it's like an array select, but it's on the knowing you've flattened the data to this two-dimensional form. And so this is a part, okay, because this is saying part beta, right? So it would be all comma beta. And then you can reconstruct the data, but you could also do, you could say you could filter by here. I filtered by the determinant. So I'm considering it as 2x2 matrices. So which elements have a negative determinant?
Okay.
So sorry,
Okay.
just as a quick question. So are you actually constructing the association there and passing it to the function, or are you taking apart the function and finding all the slots or something?
In this case, I've got, I actually called it naive, filter rows naive, and it constructs the association, Christopher. That's a really good question. Okay, but it's more of a proof of concept than actual doing. And I think it could be done, even on expression type data, it could be done, much more efficiently than this. This is sort of exploration. Okay. So
why are you calling it naive? I think that, as we move towards like more different backends like Arrow, like the actual way in which the data is stored is this association. Right?
Yes, well, I'll be showing that with Arrow in just a moment.
Yeah.
Okay, so this function itself is naive, but the actual link to Arrow is not naive, and it actually works efficiently.
Okay, but hold on. Let me just understand what this is. So Greek is essentially a level designator.
Yeah, see, that's a level designation where this is column. So that's like a part.
Well, it's a part in your flattened tabulated thing. It's a part, but conceptually, if this was a data set, it will be a level designator.
Oh, it's actually, Stephen, I think it's actually extracting a certain specific key because, I'll have examples of that as well. But the idea is if you have a keyed layer of data, basically an association, then when you do part extraction, you can just take one, like the key alpha, beta, gamma. But in this flattened approach, this part extraction translates into select. Because the keys themselves, they become data. That's an essential idea.
Right. That's what I'm trying to show. So you can select not only by part, but you could have an and I could select on both of these criterions, for example, with this function. And I'll show that with the arrow case. So the thing is, I put this note here. Note how irritating it is need to put in the data dimensions to expand back. Okay, and that's a key thing data container is going to provide for us. It's going to store these dimensional names and the data dimensions and everything all in one place. And then all these operations should be much more automatic. Okay, so now I'm so these are what I've shown here are just sort of utilities that may be useful, on their own to some extent, but the real thing I put together is this data container. Okay, so the idea is that
actually I just note that Edmund on our live stream is commenting that the resource function table set he suggests is a way of not having to construct, is a mechanism for not having to construct the explicit association. Something to look at.
Okay, I'll take a look at that. I wasn't even aware of that. So,
but that's why it's useful to have.
Yes, that's why it's exactly.
Okay. Keep going. Data
container. So the idea is we're going to have a data container, and it's going to contain an expression, and this could say be a file which you might want to read from. I'm working with actual sets of lists and associations in my examples here, but it could be a file name or some other expression, and then the idea is it's going to try and coerce it into some storage type that you've specified, and we'll probably ultimately have some kind of automatic storage type that it'll automatically pick the best thing. But at this stage, we don't have enough to put together an automatic yet. Okay, so this column list is something I developed in C. So this can work directly with C functions for some efficiency, or it can actually work with a mathematical level code as well. So in this has various properties, which will do, these properties are sort of like data structure-like properties, but ultimately there'll be commands which will get these things out. So realize these properties you see are not the final design; they're just experimental.
Hold on. So the basic point is data container can be thought of as a constructor which eats things like data sets, files, other things, potentially databases one day.
Right.
And then the second argument specifies, or some version of the second argument specifies, what the internal form that will be used. I mean, it's kind of analogous to what it's would be analogous to what Dataset is doing, except that here there's a single API that deals with this, that doesn't care what the actual internal, where the external functions being used in our language don't care about what the internal storage mechanism is.
Right, exactly. That's the fundamental idea. You've got it. Right. Okay. So I'm going to talk about some of the sort of API. One is normal, right? So normal should produce.
It's not obvious normal should not produce the data set.
Right. It may, yeah. So whether it's a data set or, here I gave it a list of associations and stuff, and whether that's a data set.
Well, the question is whether it comes back, if you feed in a data set or you feed in a file, if you say data container of a file, when you say normal of that thing, you don't want to get the file back. You want to get back some normal version.
Yes,
So
exactly.
What I'm asking is, to me, it seems like you probably want to get back by default a data set, and you can call normal again if you want to turn that data set into lists of associations. This is a detail. Let's not worry about it.
That's a detail. That can certainly, that's easy enough to do. Okay, and then another thing is particularly, this is something particularly relevant to rectangular-ish data, is part should work as well. Okay, and I've unfortunately got some bug in my code, so part's not giving exactly the same part, but it should give exactly the same as the original expression when applied to part as well.
Okay, I understand. So this data container, like data set, which also accepts parts.
Yep.
And is data container going to accept queries like data set does?
Well, that's what we ultimately want to do, and you need to figure out how to make that bridge. And I think Leonid's ideas will go a ways to doing that.
But wait a second. If you have a data set and you run part on data set, you get another data set back. So in a way, we could do the same thing and make part kind of lazy if it's on a file or something like that. And only when you do normal, you'd extract.
Yeah, but here's your point. So this was a single part. So this is a single element that I showed here. Here is, if it has dimensionality left, it returns another data container.
But doesn't dataset return a dataset even if it is a singleton? I believe it does.
No, I don't think so.
Okay.
Yeah,
fine.
I don't think that would be the right thing to do.
Right, and your sub value of data dimensions is just a hack for right now. In the future, there will be
exactly. Yeah, a lot of these things are just hacks for right now.
Okay. All right. Okay. Let's keep going.
It takes me 3 minutes to write data dimensions as a string thing, and to put that in dimensions would take 3 hours. So so we can also do transpose. Again, this is a hack. Okay,
yeah, I get it.
It's a transpose thing, but it actually what this does is it actually transposes the dimensions. And
does it actually transpose, or does it just
no? See, this is for the rectangular data. It transforms the wrapper, and so it's implicitly transformed. It's only when you do normal that it actually implements the actual transpose.
I get it. Good.
And the same applies for flatten too. So these are things that are very rectangular oriented, but they're quite useful here.
So flatten is just changing the index translation.
Yes, exactly. And it's very much like, you remember we have that weird way you can specify levels in flatten that we put together, it's exactly that. And that's what Jose uses in quantity array, something very similar to that. And it's a property you can look up called flattening. And so notice these data dimensions, I've put in, a key list with multiple things. So that keeps it compact, but that actually represents, so key list of just a list is just those keys, but with several arguments, it represents an outer product, which are these things. These are the terms in the outer product.
I think we need to look at that some more. I
we'll need to.
What you're saying, but I mean, what you're saying is, I'm not sure that's quite the right way to do it. I mean, that you're saying for a rectangular-ish thing, it's all outer products, because that's what rectangular-ish means. Is that it's an outer product of keys or whatever.
Right. So, so I've set up this filter that I'm going to show with the arrow link, and that's kind of like that naive filter I have above. And then, we need to think. So fundamental thing is so I've set up the framework for the data container, but a lot of the API is not filled in yet. So the whole big thing about the data container as I set it up is I wrote that column list thing in C, so it can work through C functions, but it can also work through something defined completely, in the Wolfram language. Okay. And it's got a registration system. So they've actually included this in the latest version of the ArrowLink package. So all I need to do is do needs ArrowLink.
Who's the they? Who's working on the ArrowLink?
Oh, that's Piotr and Rafal, I think, the image processing team.
Yeah. Okay.
And it's quite a nice packlet. It's not done yet, but it's quite nice and very efficient. And so basically the storage, the registration, as I say, I register a storage method. And this is not something users are going to use. This is what our developers will ultimately be able to use. And then there's a bunch of functions for different API type functions that it'll need to know how to do. Okay. So it's quite general. That's what I said.
General enough to include also an SQL database?
I believe so, yes. Especially if I moved away. I actually hooked up, as one example, Christopher's SQLite compiler database connection. And that's one of the things, doing that made me realize we really need to think in sort of this, a little bit more in this tabular model than the rectangular model for a lot of things. But yes, that connection wasn't very nice at this stage, but the concept does work.
By the way, what is happening to the SQLite concept of user created and user writable databases? Is that a thing? I mean, that wasn't part of the ECE meeting. Christopher, is there a plan for that?
Well, I think Leonid was working on something, so maybe he should answer. But I mean, the only things I did is I made like this demo for linking to SQLite with the compiler, which like I made in like an afternoon or something. So yeah. I mean, it wouldn't be hard. I mean, honestly, the SQLite API is pretty small and pretty simple, so it really wouldn't be hard to make like at least a packlet that lets you do that kind of thing.
Can we make sure, if nothing else, it's added as a project to the global project list?
Can I just mention that I've also built the a version of SQLite link based on library link that is already being used, at least in testing, for entity framework.
Oh, that's
teams.
right. Okay.
And in fact, there was a discussion to have maybe a more extended discussion about SQLite shortly after the release of 13.1, definitely involving Ustune.
Okay, fine. Terrific. Okay, just can somebody
one more
make
thing
sure?
I would like to add is that the other database project, the one that's compatible also with the big server-based ones, actually has writing and created databases. It's just, I mean, if we have a we design a language for writing to databases, it will be pretty quick to hook that up as well, because internally we do write to databases all the time. So for testing and so on, it's just not exposed to the top level.
Okay. So if we have a mutable version, I mean, data container is not in any way mutable. Is that true, Rob?
Well, we can decide whether it's mutable or not. I mean, it's implemented.
There might be a mutable version.
just like the data structures. So yes, there could be a mutable version.
Interesting. Very interesting. I'm sorry, just from project management point of view, can we make sure that the SQLite database is on the global project list? I believe that it is, but Aubrey, could you please check that?
Yes.
Okay. All right. Onward.
Yeah. Okay. So we load the arrow link code. That actually includes this registration command. So this just works, and then we can set up. I've set up a simple data which works with the arrow types, and I've given names, and then we can do the normal is exactly like the original, except it's converted everything to floating point. Not surprisingly, because it's well. I think what we'll be able to do, and I haven't read I think Piotr and Raphael might be able to, is you can define your own type for arrow, and so I believe we could have an expression list type or expression.
Yeah, but I mean,
type.
so arrow is basically dealing with floating point data. Is that correct?
Well, and Boolean, integer.
So why did that 16 come back as a 16 point as opposed to a 16?
Oh, because each column. So I specified the column types. It's actually I specified column types. Okay, and it needs to know what the column types are. And I think we can ultimately.
I get it. So it could be an integer. It could be a machine integer.
Yes, it could be integers, but since this had things like square root of 2 in this column, I wanted
I get it.
represent. Yeah. So
right,
that's
okay. So there's a type conversion that happened that I don't know. I mean, what do we have? Okay, if you've got a compiler type, which is what those are, right? Real 32 is a compiler type, right? And I just want to take a thing like square root of 2, the symbolic expression, and I want to cast it into that compiler type. We have a function, a cast function, which you could use at top level, correct?
We could, but there's risks of having that just evaluate, because then it becomes much harder to write compiled code.
Okay, but how do we get, go ahead.
So I think we talked about having a top level version of cast. I think the end conclusion was that we shouldn't, because basically there are lots of things that it really can't do. Like it's certainly, you can't get all the casts that the compiler does. You certainly can't get those in the top level. Maybe you can get a subset of them, but most of the useful subsets you can already get using functions like n. And of course, if you cast from a real 64 to a real 32, that's a meaningful thing in the compiler. I don't think it's really a meaningful thing in the top level.
Well, yeah. So the problem, I'll add to the problem at top level is that we don't, so our atomic types, for expression are integer, machine real, big real, so on and so forth. So we only have one concept of machine real.
Okay, but I guess my question is, for debugging purposes, even the cast from real 64 to real 32, giving a faithful cast that you could see at the top level that includes losing bits and so on, seems like a useful thing to have.
Yeah, well, this we do, it's just not very convenient. Numeric array of.
Okay, fine. I suggest that we have some utility function that does these things.
Yeah, fine. That's, yeah. So, okay. Yeah, it would be nice to have a utility function. And I'm not sure what it should do, but it'll still convert it back into a machine number. But
it'll just be with chopping off bits and things like
this. Yeah, it'll chop off the right number of bits.
Okay.
Yeah, I think that's a useful utility. I'm not sure what it should be called, but
okay, fine. I mean, we've got similar things for string encoding, for doing various kinds of sort of machine-like string encoding kinds of things. Okay, let's keep going. Yeah.
Okay, so this again, this. So now I've specified, the data. I've specified arrow type as this arrow table type, and I've also put in. I allow a third argument where you can specify sort of details of what the conversion might be, or details of the data. So here I've included dimension names, or I actually think a better name for that is level names, but I hadn't changed it yet. And then this has the column type saying how do I interpret these columns, and ultimately that should just be automatic, or we could specify any column as automatic.
But wait a minute, these are faux columns, right? These are columns after tabularization. Is that correct?
Right. Well, the columns, by the columns, we're referring to the last, this last dimension. Okay, so
Right.
these
So
are
I
the
think
1,
that's a
0,
bad
2.
name of.
Well, I think it's easy to, maybe there should be a name other than column, but I think it is it's very easy to see what the set of values is that this is referring to. If that makes sense.
Yeah.
It's not like it's pulling them from 5 different weird locations.
Right. You're right. Column is maybe a little misleading. It should be, last dimension vector types or something, but we have to come up with a good name that's clear.
Okay. All right. So let's keep going.
Okay, so parts, so with the arrow link functions they've implemented, parts just work very nicely.
Why doesn't splice work inside part? That sequence at is really horrifying.
Well, we had I think it was back in January or December, we had some meeting where we discussed a lot about splice and allowing different heads or something. And I can't remember, we never came to a very definite conclusion. But I agree.
We added to splice an extra argument.
Yeah.
For the head, but that's not what the issue here. I think splice should just work inside part.
Well, I highly disagree because it's sort of, the whole point of splice is it only expands inside of lists by default.
Yeah, you might be right.
That's the whole point. That's why sequence is difficult.
Okay, fine. Okay.
Yeah. So it's ugly, but you at least know what I mean.
I know what you mean.
Yeah. So we can do parts. The way the arrow package is implemented, we can only do parts that are sort of contiguous to each other. And then so that's a limit on rectangle. So I can't do part, I can't change this to 1, comma.
I get it. It's only span.
Because they're not. Right. It's got to be spans. Exactly. But we can also filter. And so here I'm filtering by, this level name, Greek. So that's the alpha. So that's parts. And this is actual data.
So wait a second. In this arrow setup, is this operating in our standard memory space or is it a separate process?
It's a filter. It's loaded into our memory process, isn't it?
Yeah, we are using our memory allocators as much as we can by overwriting the default arrow allocator. So theoretically, yes.
Okay, but it's in our memory space. So
yes.
Okay, so it's in our process, our memory space.
Right.
Okay.
And I don't have the proper byte count for this implemented, but the arrow is quite efficient. And I haven't shown an example, but you can actually load a file and do the same filtering thing, from a loaded file as well.
What kind of loaded file? A CSV file or something?
Well, let's see.
General import should presumably work, or there should be a way of doing this with import.
Here's a CSV file. Okay, that I have.
But how does this work? If it was an HDF file, for example, could it work? I'm just trying to understand.
Do HDF files have tabular data in them?
I don't know. I think they have some. I don't know. I'm just asking what.
I think the H is potentially problematic for us there because.
Okay, fine.
H is for hierarchical. So, but so some given storage type like this arrow table supports given, this CSV storage type, so we can do a direct. In some cases, we may have to do, if you want some particular storage type, you may have to go through.
No, I understand.
But I have to go through a few iterations.
We've got we've got hundreds of formats that we import. What you're saying is they're going to be a small subset of those that are usable directly as a file in a data container. Is that correct?
I think at the first stage, that's got to be correct. Because
fine.
What would you do with like a PNG file or something?
No, I don't know. If you look at our table, it's fine. There's certain data that we treat as, if you look at the guide page for import types, formats, there'll be there'll be a section that's called tabular data. And that's probably what's already being supported here anyway.
Yeah, that's what we want to target, I think. Yeah, exactly.
Right. But things like big JSON files might be another thing that would be relevant, for instance.
Basically, this is
JSON is supported in Arrow.
Okay, fine.
Not every flavor of it, but at least some.
Okay, that's fine. Good.
The real question is just what has a backend for Arrow?
Yeah, right, exactly. But I'm just trying to
Yeah.
make sure that we can define that. That's fine. It's probably all the things people would care about. So this is great.
I think so.
So actually, one last quick thing, which is just that I was noticing. I mean, the hash Greek thing you have there, where you're filtering based on the the level. That's presumably a lot like the supplied stuff that we've been talking about in the ILD meetings.
Yeah,
Just
and I've read my original case. I had a way of sort of automatically defining names for dimensions, and Leonoid has a way of making unique names for different hierarchies, which you'll see. But yes, I think it when I was in that supply meeting when we were talking supplied, I think this is quite. I think we should think about both of these at the same time.
Okay, this is really nice stuff, Rob. Very nice.
Okay, well, thanks. And this is yeah. So I think the big thing, the big takeout from this is we've got this thing data container that we can have different storage types for.
I think this is great. I mean, this looks like it's well on the way. Let's, because we have a limited time. Let's
let's go to Leonid.
All right. So yeah, so I think my approach has been pretty complementary to Rob's. And there are many things where we have some similar things going, but it's not really any kind of duplication. I just want to show the side of this that I've been concerned with was more about query compilation. So the goals here are listed here. Basically, the problem I was trying to address was much more narrow in scope in some sense, but wider in some other sense. So I was specifically focusing on Dataset. And the goal was to see whether we can back Dataset by various 2D formats and also import certain existing 2D formats into Dataset, and most importantly, run Dataset queries against various backends. Okay, so here are the two types of workflows that I was thinking about. One is if we have the dataset on the Wolfram language side, and we want to somehow back it by flat data, maybe persist it somewhere, and then run some dataset queries translated into appropriate query language for whatever backend the data now lives in. And then convert back for nested version for just presentational purposes, or maybe for some additional Wolfram language side operations that are not supported by the backend, but are feasible on the already computed data. And the second workflow is different, at least partly, in that there is already some existing data somewhere in a relational database, or maybe in some Parquet file, or maybe somewhere else. And we also want to be able to run dataset queries to basically represent that data in a nested form. So I want to show two examples, and if we want to go to a more conceptual level of how this flattening is happening and what's the procedure I'm following, I can explain that as well. So one example is the planets dataset, which I'm not sure if it's large enough, but I can change the magnification if
that's fine. Fine.
Okay, so basically the only thing I did to this documentation planets dataset is that I added mountains field for the planets. So otherwise it's just this documentation dataset from dataset documentation. And the important object that I'm introducing here, which can be viewed as a generalization of data dimensions introduced by Rob, is what I call tabular dataset schema, which I compute from this dataset, and which is effectively containing the bridge between the tabular data and nested data. So what's happening is that every field in the nested data set corresponds to certain unique field that is made up for the the final tabular data, the underlying tabular data that we want to build from this nested data set. And so you can see this is how this looks. So for interestingly, in this data set, and this is one of the reasons I picked it up, was that you have name collisions, like for instance, the planets and the moons both have masses and radiuses. But here, because we are making up unique fields, the end result, the final tabular data set, is going to be free of these problems of name collisions. Now, if we want to look at how this planet's sample schema looks, it's actually the nested association. So I can execute this, and you can see it's something like this. What's important about this is that this is, you can think of this thing as a addressed dataset type. So it explicitly uses dataset type system in that dataset has certain containers and atomic elements that it deals with, but it adds this mapping to unique fields in a tabular dataset, and together this is enough to actually do all the dataset flattening or unflattening that we may want to do. And the other thing which is important here is that the exact flattening and unflattening procedure may depend exactly on the specific storage backend being used. And this schema by itself doesn't say. It's abstract enough to be useful for any of those specific backends to which we want to flatten the dataset nested data or unflatten. So here is one particular implementation I'm currently using, which is to flatten to simply a list of associations. And this is what I call row-based tabular data set, but it's just to illustrate the principle. In principle, we could have as many different backends as we want, and flattening procedures adopted to those backends. So I'm creating this data set, and it creates the schema, and based on the schema, it creates a flattener, and then it creates the data. We can expand, and this shows you the mapping between the actual keys in this tabular data set and the appropriate keys in the nested data set, the fields. And also, this is how the data looks. Unfortunately, it's a little bit, yeah, but you get the idea. So it's completely flat, and it has these fields and values, but it was obtained directly from the underlying nested data. And we can also look at this data separately here if we want to. Now, there is a way to unflatten data. So there is also, if we call dataset, internally, it uses the flat data and it converts it back to the nested form. And then the thing that is most important in this approach, and where I am currently working on, is the queries. And so far, I don't have that much to show. I have the part extraction, and I can show how this works. So effectively, this part extraction actually works on tabular data and then is collected back into nested data at the end. So the resulting tabular data set is now different. If you look at its schema, you can see that it now is completely different, because it basically, some dimensions have been eaten up by extracting appropriate values here. Some dimensions remained, and also not all the rows are present. So you can see, well, actually here all rows are present, but still it is a different structure. Now, here's another example where we are extracting specific data for a specific planet. And here I'm illustrating some of the internals. So basically, each transform has schema transform and data transform. And in this case, the resulting schema is transformed, but also the data transform is non-trivial, because even though here it is a part extraction, it is converted to a selection problem in the underlying tabular data. And this is similar to what Rob was showing. So basically, what is generated here is a select. Obviously, this end is kind of superfluous here, so it had to be optimized away. But so basically, the part extraction in general is a combination of eating up certain dimensions and the selection problem. And here is the final example here, where I'm actually asking for a single value, which is the mass of the Phobos moon of the Mars. And you can see that it actually transforms into schema tells you that there is now a single value, and the data transform tells you what you have to actually apply to the underlying tabular data to actually get it. And it's generated by this query compilation procedure. Now, I'm currently working on the more sophisticated queries, and the obvious low-hanging fruits would have been various forms of select. But I intentionally decided not to show any of this today, because what I'm currently focusing on in that part of my work is to be able to compile a small subset of the core query primitives of the dataset, which are nested, including mapping and including some other things internally used. I think I have now an understanding of how to do that. That mapping is rather non-trivial, but on the other hand, if we manage to do that, then we will be able to compile a large variety of nested dataset queries into the queries against tabular data sets. And in that capacity, this work I'm doing here will also be useful to integrate with the data container, because it will provide the query compilation part for the whatever API the data container and various backends attached to data container will support. And so hopefully this will be the answer to the more sophisticated querying capabilities, to add those to the data container part that Rob is developing. And essentially, in my approach, this query execution is a compilation problem. So the ideal scenario is that if we target the SQL database, then the result of this dataset queries will be SQL queries. If we target data container, then the result of this dataset queries will be a set of a certain sequence of API calls for the API supported by data container. If we target Arrow through data container, maybe, then again, it will be a set of calls passed through data container to Arrow to actually do the proper data manipulation. But for the user will be able to use all that through the usual and convenient and well-known to the user dataset query language. Obviously, not the full query language. It will be restricted to certain things that those backends will support. But we can think of how to reconcile that with the richness of dataset querying. Perhaps dataset could also have a part that will be later executed on the resulting data on the Wolfram language side, and that will make it possible to execute things which will involve things like histogram or bar chart or other things which are explicitly rendered and executed on the Wolfram language side. Now, I may want to show a little bit about the internals just to explain.
We're going to run out of time here, so.
Okay, then we can skip it. Let me then just mention one more thing.
And then I have some questions and comments and things, but go ahead.
Sure.
Go on.
I have another example, which is kind of it's not automated yet, but I was able to use the part of this technology to import a relational database as nested dataset into Wolfram language. And so basically the idea is that, well, I mean, we start with certain relational database. I use the one that is in the documentation for relational databases. And then I take part of it and define the schema. It probably is too small to see, but.
No, it's fine. Yeah, go ahead.
So this is the same tabular dataset schema I introduced earlier. And by defining this schema, it shows how to basically translate the several tables, several relational tables in that database into the nested data set.
Yep.
And then we can actually construct this nested data set using the unflattening procedure, which is part of this technology that I've been describing. I can just show you. It probably will look pretty ugly, but this is the unflattener that has been automatically generated from this spec in the form of nested pure functions and like all this kind of stuff, which actually acts on tabular data and results into this nested data set. And my point is being that the framework I prepared is built in such a way that there is first an abstract unflattener, and then you can compile this abstract unflattener into whatever actual backend you want to use. So this is a very specific backend, which is just internal list of a socks, but it could very well be something very different. And we'll just need to compile to a different backend to get this unflattening procedure working for that. And then the goal is to run some queries. I'm not yet there, but the typical query, I have a few typical queries that we want to run against this data set. But this, I think even being able to import relational databases as an in-memory data set by itself is a valuable thing. And this part I already know how to do. So that's
cool. So I mean, but that, by the way, I mean, import should presumably be able to support that in the end.
Yeah, probably yes.
As it can, like with from olden times, it can, an access database or something, it can just import. But
yeah.
But let's zoom out for a second because we're going to run out of time here. And
sure.
We're 7 minutes over time actually. But I mean, so the big picture here is that you are creating an API to take queries of the type that are used in Dataset.
Yeah.
And both compile the query and compile and rearrange the data so that that query can be run on a different backend from our standard, in-memory system.
Exactly.
Okay.
They could be run on data container and various backends supported by it. It could potentially be run in SQL databases, and then the underlying queries will be compiled into SQL queries. Or it could be run on Mongo, for instance, and then the underlying dataset queries will be compiled into Mongo query language.
Yeah, this is very cool. So, I mean, look, the final vision is it's Dataset whose first argument is potentially some external reference to some other random database, but then you get to use the Dataset query language, and this takes care of all of the translation necessary to make that work.
Yes, and two comments on that. First of all, obviously, this query language will have to be a restricted subset of the full dataset query language available in Wolfram language because of the capabilities of those backends. Secondly, potentially, we could envision the kind of fusion so that once the backends do their work, essentially selecting and aggregating and send back the data, we potentially could envision that the remaining parts of the dataset query that exist in the query in the Wolfram language side will run on that data that we receive, so that the user will be able to use a richer set of dataset capabilities.
No, I understand. So it's essentially a callback. It's a delayed sort of action. I mean, if you can unthread the things that are not runnable on a particular backend, and have them be presented in such a way that they are then, sent back to the Wolfram language side to be run there.
Yeah.
Then that should just work.
Exactly. And so one other takeaway from here is that essentially our work with Rob is quite complementary in the sense that we have many similarities in our approaches, but in my approach, I don't even care where is this data source, because my approach is basically a compilation. And so hopefully in the ideal world, we'll have more sophisticated queries being compiled through the machinery that I presented, and then used on backends that are that are basically supported in data container. So that's how these two things can be integrated, at least conceptually.
But as far as the user is concerned, first question is, where's the data coming from? So the data could be some external thing that they never read into memory, that it's just sitting there. It's some Mongo database, it's some SQL, it's a CSV file, whatever else it is. Okay. And they then reference that through essentially through Dataset.
Yeah.
And,
so, okay.
And then apply queries to it. Getting the results. Go ahead.
Yeah, I see two scenarios here. For things which are sufficiently external, going through data container might not make sense, and it makes sense to just go directly through Dataset with the first argument being the source, just as you mentioned. Yep. For things that are sufficiently internal, or for which the synergy of using data container is high, it may make sense to register them under the data container umbrella, and then effectively my part of this thing will provide query translation or API call translation to be used against the data container API.
Right. So data container is a much more internalized thing where we're going to be doing, and you're saying what you're doing here is much more, the actual queries are going to be executed on an engine that is not our engine.
Yeah. Not necessarily our engine, may also be our engine.
Right. But data container, there are some semi-externalized engines like the Arrow engine incorporated into our engine, but fundamentally the actual computations are being done inside our engine. Yeah. Whereas your mechanism allows the possibility, as for the SQL database stuff already built, to do the operations in a different engine. Yeah. Potentially on different machines, et cetera, et cetera, et cetera.
Yeah. And also for internal things like data container, for more sophisticated queries, it will provide the same kind of capability to translate these sophisticated queries into the set of data container API calls.
I see. So the data container API is another backend like SQL for your stuff. And so then the question is, so what's the relationship between compilation technology for the standard compiler and this, which is another compiler that has different kind of data type concepts, or somewhat related, but not quite the same?
I would say that the relationship is, in the zeroth approximation, there is almost none. But if we decide to try augmenting certain external backends with, for instance, Wolfram language compiled functions, or if we decide to use things closer with data container, in those places, the relationship will become more important, and at least through the type systems, they will be obviously, they have to be merged, or maybe a compiler type system will be used for this stuff. But in some sense, this relationship is somewhat similar to how the databases project compiler to SQL relates to the Wolfram language compiler. In the zeroth approximation, there is no relation. But as long as we want to allow external databases run some callbacks to the kernel, for instance, which is, well, we can imagine this might extend. So once we reach that point, then they will become interacting.
Yeah, and once we have just-in-time compilation, those kernel callbacks will probably be pretty efficient. But then the question is, for these external things, I would imagine, if I'm not wrong, things like Spark and so on do allow you to send external code to be executed on separate database nodes, do they not?
Well, I can't answer for Spark, but I can answer that some number of relational databases allow C-level callbacks.
But but the question is, can you push a dynamic library, for example, to the database server to be run on the database server?
I think you can do similar things for Postgres and for, I'm not sure whether every database supports that, but maybe most databases support
Right,
C-level
so that's a
API.
super interesting thing that we could imagine, and even in the most sophisticated version, I mean, this would solve another problem, which is being able to do distributed databases, like with Spark or whatever the latest thing is in that regard. With our standalone technology, you could even imagine pushing a complete Wolfram engine with some compiled code that's being run, so that you could actually do arbitrary queries in the distributed, distributed database.
Well, there's a bit of a problem in terms of permissions. On the other hand, I am pretty sure you can do that with SQLite, which sits on your machine. And it has an external function interface.
Exactly. And this is something I also wanted to mention. There is SQLite, and there is a very modern, even much faster database, actually a couple of them, which are free and open source as well, and can be used for, like DuckDB, which is a columnar version of SQLite. That's how they position it. And also there is a TileDB, which is an array-based in-process database. These are something like, at least for SQLite and DuckDB, these are file-based databases which could potentially even be used in the cloud. And with the callbacks, we could create an incredible data processing solution for individual users who can just use.
Yeah, that's very cool.
Yeah,
we are deeply run out of time. This is really nice. We need to continue this series of meetings. But if other people have other comments, they can give them. But I need to disappear. Anybody have a quick thing to say here? I mean, other than this seems to be going really well. Lots of work to be done. Seems like Rob's stuff is closer to being deliverable than Leonid's. But
the one comment I'd like to make is that there's nothing particular in the data container as I've set it up that requires it to be, in Wolfram language process memory.
Okay.
It's a reference, basically. It could have any reference you want.
Okay. Very cool stuff. All right, we should wrap up here for now. To be continued another time.